the reception hall, we have some printed materials concerning CERN, and with these two kinds. If you are interested, you will take with you after the presentation here. Be careful, they are not only in English, we have in several languages. And the last thing, probably not the least, if you have cameras with you, you could take photos everywhere you'd like. No restrictions of any kind, because there are no secrets here at CERN. So that's all about the organization of your visit today. Now, if you have no questions concerning only the organization of the visit, I could start immediately with the presentation of CERN. No questions. So I hope you have a private bus. We'll need it later on in about 45 minutes or 1 hour. The bus will be here. Yeah. Okay. So before starting the presentation, I'll change the lights a little bit because it seems to me that there's too much light on the screen and you couldn't see it very well. So, but finally it's up to you to decide. Do you think it's better this way? Oh yeah, well, we could close here a little bit. But not completely because there is no ventilation system. So, the presentation started with the name of CERN. What does it mean exactly? Probably you know it already. It's a French abbreviation which stands for European Center for Nuclear Research in French. You see the 4 letters you had here. So, first of all, why European Center? Why CERN has been created only 10 years after the end of the Second World War as an European Center? Why not national centers in Britain, in Switzerland, in France, everywhere in Europe? The reason is very simple. You know probably from the history that large part of Europe has been devastated, ruined by the war, and after the war there was no money for the science. And when several years later the situation improved a little bit and it was possible again to give some money for the scientific research, the amount of money available for this purpose in each European country was so modest that it was necessary to put them together to be able to restart approximately, at least approximately on the same level as in the United States. And the discussions between physicists and politicians of that time to create CERN have started already in 1947-48, but the convention for the creation of CERN has been signed in 1953 and validated the following year, 1954, by the governments of the future member countries. And that's why the year 1954 is considered today as a birth date of CERN. The second part of this name, nuclear research, especially the word nuclear, is making reference to a very important discovery in the modern physics, the discovery of the nuclear chain reaction just before the war, discovery on the basis of which very soon, only several years later, the atomic bomb has been created, and in the same time the nuclear reactors produce energy. And there is no doubt that this discovery has been so spectacular for the people of that time that years later everything concerning the modern physics was automatically called nuclear. But in 1954, when CERN was created, this nuclear era was belonging to the history of the modern science, and CERN has started its activities directly studying the particles, the so-called still at that time elementary particles, which means one level below, one level even deeper into the matter, not on nuclear but on subnuclear level into the matter. That's why this name was not very appropriate. It had to be changed, and moreover it was scaring the people here in Switzerland as well as on the other side of the border in France. And the name was really changed, but not immediately, about 30 years later, in the middle of the 80s, and CERN is officially called today European Organization for Particle Physics. Nevertheless, as you have seen probably already, this abbreviation CERN is still used everywhere, not only by the people working here, but also in no official documents of CERN. The reason is that this is a trademark of CERN, a very special name of reference and tradition. What we are doing here at CERN, it should be stressed from the very beginning, fundamental research. Fundamental research, which means research concerning the laws of the nature, how the nature is done, how the nature is acting, how the nature is proceeding. The fundamental research is prompted by the deep-rooted need of man to know the world around him, and the fundamental knowledge is part of our civilization today, but it does not mean necessarily that the fundamental research is only a question of scientific curiosity, because the results of this research, the discoveries, when we have discoveries, will become sooner or later the basis of new technologies of the future. These results, these discoveries are published as soon as possible in specialized scientific journals, which means they are becoming available to everybody. They are becoming part of the public domain. That's why CERN is financed with public money coming from the taxpayers of the European member countries of CERN. Which are these European member countries of CERN? Here they are, you could see them on this map of Europe. Today, CERN has already 20 member countries, but more than 58 years ago, CERN has started its activities with only 12 member countries, all of them from Western Europe, including Britain, of course. And later on, other countries joined the organization, starting in '59 with Austria, after the end of the Soviet occupation there. Then, in the middle of the '80s, Spain and Portugal, after the end of the dictatorial regimes in these two countries. And finally, at the beginning of the '90s, 5 East European countries joined CERN very soon after the falling down of the communist regimes in these countries. So how these 20 countries are contributing to the budget of CERN. The budget of CERN, which is about 1,200,000,000 per year. Each one of these 20 countries must contribute according to the population, to the richness of the country, which means according to the internal national product. Germany is paying 21% of the budget, followed by the other big European countries. Britain, France, Italy with 16, 15, 13% for Italy. Switzerland is paying 2.5%. Finally, these European countries, below 1% each country for the moment. What CERN is doing with this money? CERN is using the budget to build up and maintain new particle accelerators, to build up and maintain the infrastructures necessary for these accelerators. Finally, CERN must pay the salaries of the people working here at CERN, employed by CERN. At this moment, 2,300, 2,500 people. And CERN is today the biggest laboratory for the particle physics in the world, a major European success. But in the same time, CERN is a center of excellence in the science, attracting a lot of physicists from the other countries, not only from the European member countries. CERN is always an European organization, as it has been created almost 60 years ago, but CERN is open for everybody. And the physicists from the other countries could come here as well to participate in the experiments and collaborate with their European colleagues. Of course, this is not free of charge, because the institutes and universities sending these physicists here must contribute to the financement of CERN as well. They are not contributing directly to the budget of CERN as the 20 member countries, but only to the budget of the experiments these physicists are participating. And you could see on the next map the ever-growing number of physicists from different countries working here. On the left, you have the number of the physicists from the European member countries. But as I told you already, we have a lot of physicists from the other countries outside Europe as well. If you take a look here, for example, from United States, we have not 1,300 physicists as indicated here, but already 1,600 physicists from the beginning of last year. The Russians are more than 1,000, but also physicists from a lot of other countries. We could estimate today that we have here physicists from more than 100 different countries working with us. So that was about CERN, foundation, member countries, budget, general questions of this kind. Now, I told you from the very beginning, I tried to stress as well, that what we are doing here is fundamental research. Of course, it's absolutely true, but what does it mean exactly concerning the particle physics? Which are the main questions, the main problems the physicists are trying to resolve here already several decades? Here they are, these main questions. First of all, which are the elementary constituents of the matter? Then which are the fundamental forces controlling them and defining their behavior? Finally, which is the role of these constituents and forces into the origin and the structure, the evolution as well of our universe. So several words to explain these questions, or for you just to remind you a little bit your knowledge you have already concerning the structure of the matter. Well, you know, of course, that everything around us is not continuous but constituted of atoms, which is a very old idea coming to us from the ancient Greece, but for many centuries it was only a philosophical idea, because the real existence of the atoms has been proved scientifically, which means by different experiments, only about 100 years ago, at the beginning of the last century. And the studies of that time have shown already that atoms are almost empty. They have only one nucleus in the middle, very small, comparing the volume of the atom, and electrons turning around and charged with negative electricity. And the nuclei are not homogeneous either. They contain two kinds of particles: protons, positively charged, neutrons, which are neutral. And after the protons and the neutrons, a very large number of particles have been discovered during the first half of the 20th century and up to the end of the 1960s. At the beginning, several, then several tens, then hundreds, finally thousands. But most of these particles do not exist really in the nature, because their time of life is extremely limited. So once created, these particles are disintegrated very, very rapidly, for a fraction of a second, or million, billionth of a second, to other particles, and finally to stable particles. And that's why probably we should not say the physicists discovered them, because these particles do not exist in the nature. They could not be discovered. But the physicists rather recreated them in their laboratories, using interactions between particles already well known. And today here at CERN we're doing exactly the same thing, but using tools much more advanced, much more sophisticated, namely our big particle accelerators. But by the end of the 1960s, the number of these so-called elementary particles, elementary in the sense with no internal structures, as point-like objects, the number of these so-called elementary particles was already so high that the physicists started to have some doubts that all these particles are really elementary. They suppose that most of them contain even smaller constituents inside. This smaller constituents was called quarks, and from the beginning of the 1970s, the existence of the quarks has been proved by different experiments. So after all these changes, discoveries during the 20th century, what is left today as basic constituents of the matter? Here they are. You could see them on this table. On the left you have the particles, on the right the quarks. Today we know only 6 elementary particles. All the others are containing quarks inside, so they are not really elementary. For us, for the human beings in general, the particles and the quarks on this horizontal line in book over here are the most important, because everything around us is constituted of these elements. What we have around us, we have atoms, inside each atom nucleus, inside each nucleus protons and neutrons. The protons and the neutrons are exactly here in the table. Inside each proton we have 2 quarks up, 1 quark down, and inside each neutron vice versa, 2 quarks down, 1 quark up. Around the nucleus are turning the electrons. The electron is here as well on the same horizontal blue line. And here we have one additional particle called electron neutrino, very important for the exchanges between the protons and the neutrons, but all the other particles are not stable. They are disintegrated very, very rapidly. Finally, is that all we know today? 6 particles, 6 quarks, which give us 12 basic constituents. Well, not exactly, because you know already that each particle you see here on the left has a respective antiparticle. What is an antiparticle? It's a particle as well, which the same parameters as the corresponding particle, except one which is in opposite. And very often this is the electrical charge. For example, the electron. Let's take the electron. The antiparticle of the electron exists. This is the anti-electron. The electron is negative, with negative electrical charge. The anti-electron is positive, and that's why it's called very often positron. But all the other parameters of these 2 particles are the same. The masses, for example, of the electrons and the positrons are strictly equal. So this is true for the particles. This is also for the quarks. Each quark you see here has a respective antiquark. That's why we must multiply by 2 these basic constituents. We know 24 basic constituents of the matter today. The particles and the quarks are forming the matter, the antiparticles and the antiquarks are forming what we are calling the antimatter. To form the matter and the antimatter, of course, these basic constituents are very, very important, but we need something else to keep them together. To define their behavior, this something else, these are the main forces in the nature. And during the 20th century, man has known 4 forces, and this is the gravitation, the electromagnetic force, the weak force pushing the particles to disintegrate, finally the strong force which is keeping the quarks inside the particles, and it's not possible to take them away outside these particles. It's never possible to get free quarks in the nature. Now, with the particles and the forces, I'll stop here. We don't need more information, but of course, if you have some questions in this direction during our visit today, don't hesitate to ask your guides. But the general question here is how the physicists discovered all this, how the physicists established all these facts. Well, they have done a lot of experiments, and during the last several decades, mainly experiments with the big particle accelerators. How the physicists will continue to work to make new discoveries, there is no doubt. They will continue with the experiments with the big accelerators, but accelerators even bigger, even more powerful than the accelerators we have already today. The accelerators which exist today are huge. They are really huge, which means very difficult to build up, but also very expensive to build up, very expensive to maintain during long years, during decades for some of them. Nevertheless, the big particle accelerators are absolutely indispensable for the particle physics. So why? I'll show you the answer, even 2 answers to this question. Well, here they are. So, first of all, we are using the big particle accelerators to probe the matter at short distances. What does it mean exactly? With accelerated particles, we could fire and penetrate inside some new particles, relatively new particles. We still don't know very well to discover the internal structures and different parameters of these new particles. And the second reason, much more important for us today here at CERN, due to the big particle accelerators, we could create new particles. New particles is not completely true. These particles are new for us, but they existed already for a very short time after the Big Bang, this explosion which created our universe almost 14 billion years ago. But they do not exist anymore in the nature, and if we would like to study them, we must first of all recreate them, and this could be done only with the big particle accelerators. So this possibility to recreate particles which do not exist anymore in the nature is based on this famous formula of Einstein, established by him more than 100 years ago in 1905, when he was working here in Switzerland in Bern. This formula is part of his theory of relativity, but it's a very simple one, showing that in the particle physics, the energy of the particles is proportional to their masses. Proportional because the c squared is the velocity of the light, which is a constant. But this formula has a little bit deeper meaning, showing as well that in the particle physics there is no big difference between the energy and the mass of the particles. Both are equivalent according to Einstein, which means that the energy of the particles could be easily transformed to mass, and the mass back to energy, and that's exactly what is happening all the time inside our big particle accelerators. Particles are accelerated, the energy of these particles is increasing. In the same time, the masses of the accelerated particles are increasing as well. Both are proportional. We could not increase the energy only, not changing the mass. And the mass of the accelerated particles is increasing not 2, 3 times or 10 times, but hundreds, even thousands of times. It depends, of course, how powerful the accelerator is. And then these particles with very high masses due to the acceleration are entering in interactions inside our accelerators. Their masses are transformed to energy, which is not stable, and this energy is giving but immediate new masses, new particles, and higher this energy of acceleration is, here are the masses of the newly created particles, created by the interactions. Exactly this kind of particles we are looking for now. Particles with very high masses which do not exist anymore in the nature. How the particles are accelerated, you will see this today during your visit, especially on the second side. But generally speaking, to accelerate the particles, we are using the electrical and magnetic fields. When these electrical and magnetic fields are arranged on one straight line, in this case we have the so-called linear accelerators. These linear accelerators are very similar to a TV set, but not the modern plasma or LCD screens we have now, but TV sets with cathode tubes which still existed several years ago. In each TV set of this kind there is a wire, high temperature, emitting electrons. The electrons are forming a beam accelerated with electrical field, and around the beam, here at this region, there is a complicated system of magnets to deviate the beam very rapidly and to modulate it, and this way the beam will create on the screen the image we're watching from the other side. But very early in the 20th century, already 1930, some physicists had the idea to make the particles run in round. So this way, the particles will pass through the same electrical fields, the same magnetic fields many times, and the energy of these particles will increase a lot without exceptional increasing of the cost to build up these kind of accelerators. This is called, of course, circular accelerator. When the energy of the particles is already high enough, the beam of particles must be taken out of this circular trajectory to be sent to a fixed target of different materials. The accelerated particles will produce interactions with the nuclei of these materials, and the physicists will analyze these interactions. And the last idea, we could increase even more, we could practically double the energy of acceleration, adding a second beam in parallel and very near to the first one, but the particles in this second beam